Regarding today's presentation, we're gonna talk about what is a substructure, the parts of the substructure, and we're gonna have the different Midas programs to analyze and design those parts. So let's begin with the substructure. So what is the substructure? As you might know, the substructure is the part of the structure that is in charge of transmitting the load to the ground. Every structural system, the main goal of every structural system is transferring the load to the ground, and this is mostly done through the substructure itself. It is composed of the bearings, piers, abutments, and the foundation. Here's a small diagram that shows you each part of the entire system. We have the superstructure on top, usually for bridges, which transfer the load from the live load and some part of the dead load to the bearings, which is where usually the substructure starts. With the bearings, then the load is transferred to the piers and then to the foundation, which is at the end, transferring the load to the ground. Regarding the parts of the substructure, we have the bearings of the bridge. The main function of the bearings is to transfer the forces from the superstructure to the substructure. It also provides rotational and or translational restraints depending on the type of bearing, and they are basically used to accommodate some types of deformations. These deformations occur due to various methods, such as various effects, such as the thermal expansion, the elastic deformation under live load, the seismic forces, and also wind loading, settlement of the supports, the creep and the shrinkage of the concrete, depending on the type of material and the location of the project. The bridge bearings, different types of bridge bearings are used. Based on the degree of freedom, the type of materials, and the bridge bearings, they can be classified under these: the sliding bearing, the rocker or roller bearing, the knuckle bearings, elastometric, and the POT bearings. The sliding bearings is basically a system of two plates, one sliding over the other, that makes one of the, this is one of the simplest ones, the simplest type of bearings, which is the one that I'm showing here, and they permit the translation in the longitudinal and transverse directions. So unless specifically restrained in any of these directions is provided, then these are the different possibilities of motion or translation in these type of bearing. They're usually the surface is mild steel over mild steel, and they differ in the coefficient of friction depending on the type of material. You can use mild steel over phosphor bronze or PTFE, depending on the type of sliding that you want to have. We also have the roller bearing, as you can see here, and they consist of a single or multiple rollers depending upon the load to be transmitted and the allowable translation that you want. Usually they're made out of forged steel, and they look something like this. You have the single roller as this one, and also multiple roller, as you can see here. We also have the rocker bearings, which are these, as you can see in the slide. They consist of assembly of a sole plate, a pin and a plate assembly. A rocker plate, and is based on a plate on which the rocker plate rests, which is this plate right here. So this is a little diagram of how they look like, and here you can see pictures of those type of bearings. We also have the knuckle pin bearing. These are a combination of a rocker and a roller type of bearing, which can cater to the translation as well as the rotation. It consists of a saddle plate assembly resting on a knuckle, which is rigidly attached to knuckle slab, which further translates on a set of rollers, which is these ones that you find here. And they're linked by plates, and the whole assembly rests on the base plates, which are these plates that you can see here. This is just the knuckle pin bearing, which is the combination as I mentioned, and just so you can have an idea of it. The direction of allowable rotation depends on the type of knuckle. You have the cylindrical knuckle, as you can see here, and it allows unidirectional rotation. You also have the spherical bearing, which is this one. It allows multi-directional rotation, as you can see in these diagrams. And also you have the knuckle leaf bearings, which is similar to a pin rocker bearing, but it has multiple leaves instead of a single sole plate, which are these, as you can see here. Then we have the elastometric bearings, which are the most common, widely used type of bearings for bridges, and they comprise of elastomers with polymetric substances after vulcanization of rubber. They're basically made out of rubber, part of them, and the pads can be directly used as plain elastometric bearings, and then this is an image of it. They of course have some type of reinforcement, usually made out of steel, and there are three types: the plain elastometric bearings, the steel reinforced elastometric bearing, and the fiber reinforced elastometric bearings. These are easily modeled in the program, and you can use different types of elements, which I'm gonna talk about later, to do the analysis of these type of bearings, or to simulate the behavior. Then we have the pier and the abutments in the bridge. Their main focus is this part of the bridge, which the part of the load pass between the superstructure and the foundation. Basically, what they do is they take the loads from the bearings and then they transfer it to the foundation through different types of system. They transfer the vertical load, and they resist the horizontal forces acting on the bridge, usually. The abutments, in addition to the functions of the piers, they're used at the ends of the bridges, and they retain the embankment, as well as they at the end of the bridge they work as an entire system. In multi-span bridges, the end of the superstructure is supported over abutments, where the intermediate spans rest over piers, as you can see here. These are different types of piers, and these are the abutments at the end of the bridge. So basically, the piers resist and transfer the vertical and horizontal loads to the foundations, and the abutment, they, as I mentioned, retain the embankments at the end of the bridge. There are different types of piers. They can be classified as per their connectivity with the superstructure, as monolithic or integral type, and cantilever type. For example, the superstructure and substructure are separated, since, as I mentioned, by bearings. So another classification is done based on their sectional shape. Either monolithic is when they're not supported by bearings, and when they have the bearings is kind of a cantilever one. But then regarding their sectional shape, we have the solid hollow, cellular type. We have the trestle type, hammerhead, and the frame type of pier. For example, the solid type, hollow, and cellular types, which are the ones shown here for the based on the sectional shape, they can be of different cross-sectional shapes and are often used as a water crossing, since they can be constructed to proportions that are both slender and streamlined. For the construction of massive piers carrying multi-lane traffic, these type of piers are economical. For example, the cellular one, and they just use the reinforced concrete, which they can save you some money using these types, with the hollows portions. We have the trestle type, which is usually composed of reinforced concrete column with a connecting cap on the top, and they can be either used to support a steel girder superstructure, or can be used as an integral pier, where the cast-in-place construction technique is used. These are the most popular forms of piers in the modern highway systems. You also have the hammerhead, which consists of a massive single pier with a cantilever pier caps on opposite sides. This is usually used for elevated highways as well. And then we have the RC frame type, which is something like this one. Is more aesthetical and rigid due to the monolithic joints, which is, as you can see here, and they're ideally suited to reduce the span length of the main girders. As you can see here, there's a little portion of the pier right here, but this type of construction requires two expansion joints here, so it has its pros and cons. Then we have the abutments. The abutments can also be classified, let's say, into the closed cantilever, the high abutments, which are the wall type and counterfront, the stub, pedestal, and the integral abutments with the piles or with the open foundation. The closed cantilever abutment consists of a vertical arm and rigidly fixed to a horizontal base footing. We also have some diagrams here of different types of abutments. As you can see here, we have the stub abutments, which are relatively short, as you can see here, and they are constructed after the embankment have been completed. The post-construction settlements are minimized. These abutments may rest on a shallow foundation or on piles, as you can see here. And then we have the pedestals, as you can see here with the diagrams. These are short stub type of abutments supported on multiple stem pedestals, as you can see here. And then we have one that is used very often, which is the integral abutments. Probably you guys know about it. And they are connected to the superstructure rigidly, without any joints for expansion or contraction. They can be wall type of abutment resting on a shallow foundation. But the more common type is integral abutment in a stub type provided with the substructure integrity and resting on flexible piles, which is the one like this one shown in this image below. The major advantage of this type of abutments is the lower construction and maintenance cost. But the problem with the integral abutment is that the cyclic lateral expansion and contraction due to the temperature stresses, they can result sometimes in cracking or buckling, which, that effect must be accounted for in the design portion of these type of abutments. Talking about a little bit of the design portion of the piers, the design of a pier or a column is performed to fulfill the strength and the serviceability requirements, as you might know. For design of the piers, the first step is basically to calculate the design loads acting on the pier. So in order to do that, we have to take into account the dead loads, live loads, wind loads, and centrifugal forces from the superstructure, longitudinal forces, ice, pressure, earthquake, thermal, shrinkage forces, vehicle collision loads, and so on, depending on the location of the project, the type of bridge that you're using. These loads come into account and they need to be considered in the design. A lot of engineers use software foundation only or substructure only programs to do the design of the different type of elements on the substructure, and they are acceptable. They provide acceptable results. Some codes accept those type of analysis, and today we're gonna focus a little bit more on those, specifically the substructure parts, like how we can model them using Midas, even though Midas can handle both superstructure and substructure, but we're gonna focus on how to do the substructure only portion. Regarding the piers, of the design of the piers, just an overview. The flexural resistance of the concrete is dependent on the axial force acting on the member. So what we usually get from the the type of the analysis of or the design of the pier is the interaction diagrams for the design of the compression members, which are the piers usually. They're usually created assuming a series of strains distribution and computing the corresponding P and M values. For the pure compression, we have different factors that we can use. Also for the pure flexure and biaxial bending, just to give you like a little background on it. And this is basically an interaction diagram that we can get from our programs. I'm gonna show you in a little bit how you can get it. But just to give you an overview, the point 8 represents the pure compression. Point E represents pure flexure, which is this one. From A to C, compression failure occurs. From C to E, tension failure occurs. Point C represents the balanced strain condition, which corresponds to the strain distribution where the extreme concrete strain reaches 0.003 and the reinforcement reaches yield at the same time. At this condition, the section has the highest moment capacity, as you can see here, axial and moment at this portion. Then we have the shear strength calculation that we also need to consider in this type of programs, in this type of elements. And just to give you an idea of how you can calculate the shear strength, the nominal shear is provided basically with the concrete subjected to the flexure and axial compression. We have different values and factors for F prime C, the area, the effective width and the depth taken into consideration. And then we have the resistance of the concrete with the different factors also. We also can consider the shear resistance due to the steel that we provide for reinforcement, and then we basically add them up. The shear resistance of the concrete plus the shear resistance of the steel, and then we have more or less a nominal resistance. For the abutments, we have to consider different types of loading, and also depending on the type of abutment that we're using, there's some factors, as I mentioned earlier, that need to be considered. We have to consider dead loads. We have to consider live load, impact winds, centrifugal forces. Sometimes the expansion and contraction of the, in case that we don't have any joints, earthquake loadings, and so on. Depending on the location of the project, also there are some other type of loads that need to be considered. For the abutments specifically, there are different loads that need to be considered as main loads, which are the soil pressure that acts on the pier. Also for the earth pressure, the earthquake pressures that can act on the pier as well. There are some factors in each code that provides us with the calculation of the different loading. Also for the abutments, we have to check the stability. There are different stability checks corresponding to the various modes of failure carried out, and with different factors of safety specified as per different codes, or the engineer can choose which ones is going to be their factor of safety. We have the sliding failure, the overturning failure, the bearing failure, and the deep-seated sliding failure, as you can see some diagrams here. For the design loads, you have to first get the preliminary dimensions of the stem, toe and heel, and then you have to calculate the design loads. They're amplified with each of their factors depending on the code that you're using. You have to compute the dead load effects, the dead load from the superstructure, and sometimes the programs are used to do this type of analysis. You just bring the point loads from the superstructure, and then you just design with that. This is again unacceptable, but not the best procedure to do it. And I'm gonna show you how you can simulate these using Midas programs. First, I'm gonna do the modeling of a pier, so you can have an idea of how you can bring the reactions basically from the superstructure and bring them into the program. We're gonna do a pier like this one. This is one of the typical piers that are used, or the most used piers, as I mentioned earlier, and we're gonna see how we can model it using Midas Civil. This is the graphical user interface of Midas Civil. We have the ribbon menu on the top. We have created this ribbon menu as the menu in AutoCAD or Microsoft Office programs, in which you have the different tabs, and each one of the tabs shows you the different functions related to the tabs, such as the node and element. You can create the nodes and elements, the properties such as the material properties, the section properties, and so on, boundary conditions, loadings. And the way of working in the program is always from left to right. So if you want to apply loads, for example, you go to static load cases on the left, define the load cases, and then you go so on to the right and define each one of the functions. We also have something called the tree menu. In the tree menu, we have the different tables from the model. We have the work tree, in which all the things that are implemented in the model are gonna be displayed. We have the different groups, and also the report function, where we can generate a dynamic report in the program. We also have a function called the tags pane that shows you the different types of procedure or the required step for each one of the analysis in the program. We have also the message window. This is how the program communicates with us. It's not a black like a black box, but the program tells us if there is an issue in the model, or if there is something that is not behaving properly, if there is an error. That's how the program communicates with us. We have the unit systems here at the bottom, and we have the different views, the different views on the right part of the graphical user interface. The first thing that we're gonna do is we're going to define the properties, such as the materials and the sections that we're gonna use for this pier. So we can go to the properties tab, or we can just right click on the model window, and we can just define materials, go to the properties function and define the materials right there. In Midas Civil, we have different materials that we can use for the analysis. We have steel, concrete, as you can see, SRC, which is the steel reinforced concrete, and we also have the user defined function that you can use for the analysis, or any type of projects that you're using. In this case, we're gonna use concrete. And in the program, we have different standards that we can use. We have international codes, European codes, Asian codes, and we have the ASTM, Canadian also. In this case, what we're gonna do is we're gonna use the 5000 psi concrete, and then we just hit OK. Here, as you can see, as I define the concrete, it is listed here. Everything that we define is going to be added to this list. That way, for example, I can see what other users did, and I can easily check their models. As a part of the technical support team, we provide that service. And from here, I use it a lot because I can see what the users did and what they have assigned to the model, and so on. We also have the section tab. We're gonna add a section now, and we can define it right here. You can either do it here after you define the properties, or you can do it here during the section portion. So let's add a new section, and we're gonna add we have different types of section in the program. We have the typical sections from, let's say, AISC. We have the different sections that we can use for piers also. We have SRC sections that we can use, as you can see here. We also have combined sections also. We have PSC for the pre-stressing bridges. We have different types of sections that we can use. Composite as well. As you can see here, we have different types of composite section, and we also have the tapered one. That is the one that we will be using today. In this case, we're gonna add a tapered section with the solid rectangle, and we're gonna assign the name for it. And then we're gonna give the values for the I node and the J node. For the I node and for the J node, you can define the variation as per within the tapered section. It can be linear, it can be parabolic or cubic, and in this case we're gonna change the offset, which is this point right here, the insertion point, to the center top, which is kind of located at the top. And then we can just hit apply, and that will define that section. Then we have the to define the cap mid, and for that we're gonna use the DB user function or tab. Here we can define the solid rectangle again and name it, and then just define the properties, the base and the height of it. Also, let's change this one to center top and apply. And then we're gonna define the pier. So we're gonna use a solid round for the pier and assign the name of it. We're gonna do a 1.5 meter diameter for it. And this one we're gonna change it to center, so we can insert it from the center point of it. Here you can see the 3 different sections that we have defined. And what we're gonna do now is we're gonna start defining the nodes to generate the model. So in order for us to do that, what I'm gonna do is I'm gonna create nodes using this function for create nodes, and I'm gonna create one in the origin, which is 0, 0, 0, and I'm gonna copy it at a distance of 3.6 meters in the y direction, which will be the transverse direction. I hit apply, and here if I use this view, I can see the 3 nodes or the 5 nodes generated, as you can see here. Let me just zoom in a little bit just to show you that the 5 nodes are generated. After that, what I'm gonna do is I'm going to generate some other nodes in which I'm gonna connect later on to generate the entire pier. So in order for me to do that, what I'm gonna do is I'm gonna first select this node using the select by window function, and I'm going to translate this node using the translate node function. I can use or locate that function in the drop down menu right here, or I can use this function right here for the translation. I want to copy it on equal distances in the y direction, which is this direction, transverse direction, and I can specify the program the distances that I'm gonna use. From here I can translate it and the program will generate the nodes for me. Let me just change the view to the lateral view so you can see them here. Just put the node number here, and then I'm gonna select this node right here and do the same but in the negative direction, which is gonna be these 2 right here. After that, what I'm gonna do is I'm gonna generate the elements. These elements are gonna be the cap, and what I can do is I can just directly go to the element tab right here and use the create element function. Here I can select the cap end and the material that I'm gonna use. I'm gonna use a type of element which is the general beam in the program, and then I'm gonna start generating it from left to right and then from right to left, so I can create the tapered part. So from left to right, this part right here, and from right to left, these 2.6 meters on the left, on the right side. From there, what I'm gonna do is I'm gonna create the mid cap. I'm just gonna change the section right here for cap mid, and then I'm gonna start it from here until the end, which is gonna give me something like this. Let me just change the view so you can have an idea of how it is looking right now. Then from there, what I'm gonna do is I'm gonna generate a tapered group. The program automatically generates the tapered portion of the section. So in order for me to do that, what I'm gonna do is I'm just gonna show you this function, which is the tapered group, and then from there we can generate the tapered section. So let's call the left end, and let's choose these 2 elements right here, and let's do a variation, a linear variation, and just add it. The program will do something like this one. and then I'm just gonna create the right portion and select these two elements right here. Close it here, and then I can have this bend cap. From there, what I'm gonna do is I'm going to generate some other nodes so I can create the piers from them. So I'm gonna select node 4 and 2, and I'm going to translate them into unequal distances in the z direction, which is the vertical direction. And then this will give me these nodes at the bottom of the pier, of the cap, and then the nodes to connect the columns. Columns have 10 meters height, and then from there I can go back to create the elements using the create element function, and I can just connect with the pier section, connect these two nodes right here. There's one right here and the other one right there. And from there I can generate a pier cap, as you can see here, with an entire pier. After that, what I'm gonna do is I'm going to create elastic links to connect the nodes. If you take out the hidden view, you're gonna see that the nodes are not really connected. You know, the band cap is floating basically. So what I'm gonna do is I'm going to create a rigid connection in between them so that the program can connect them together and form an entire system. So in this case, what I'm gonna do is I'm gonna go to the boundary tab and I'm gonna use an elastic link. This elastic link is gonna be of rigid type. We have different types of links that we can use to connect or simulate different type of bearings or a rigid connection, tension only, compression only behaviors. But in this case, what I'm gonna do is I'm going to create the elastic link, and this is going to have I can either copy it and it will copy them together, or I can just select two nodes and the program will do something like this. Now they are connected to each other, the bend cap and the piers, and then from there what I'm gonna do is I'm going to generate the supports of the structure. So in order for me to do that, I'm going to select the two nodes at the bottom of the pier, and I'm going to define the supports using this function. I'm going to restrain, here you can restrain certain degrees of freedom or to represent different type of, like a pin bearing, fixed bearing, and so on. In this case, I'm going to restrain all the degrees of freedom to just, make a fixed connection for the pier portion. If I hit apply, you're gonna see here that the program generates hexagons, each of made out of 6 triangles. Each one of the triangles represents a degree of freedom. The 3 triangles on the right are the translational degrees of freedom, and the 3 triangles on the left are the rotational degrees of freedoms in the XYZ with the clockwise direction. From there, what I'm gonna do is I'm going to generate a load just to show you the way that you are currently doing this type of analysis. So you can do, as I mentioned, you can go quickly to the load tab, define the static load cases, and here let's just define a dead load. Here you can define the different types of loading that come into account for the bridge design. In this case, we're gonna select the dead load just to show, but as you can add different types such as the earth pressure or horizontal earth. You can also do the earthquakes, you can do pre-stressing, you can do braking loads, centrifugal forces, you can do as many as you want, and then the program can automatically generate the load combinations from there. So In this case, just to show, I'm gonna do the dead load, and I'm gonna take the results from another superstructure analysis and just put them in this pier just to do the analysis of it as it is itself. With this load, the program can generate the load combinations automatically as per ASHTO, so you guys don't have to worry about it. The program has auto generation of load combinations. You can also do the design of it using ASHTO's LRFD, and you know we have different codes that you can use in the program. After you define the dead load case, let's just do the loading as nodal loads. Let's just apply vertical nodal loads from the dead load of the superstructure. And in order for me to do that, what I'm gonna do is I'm going to define forces in the C direction, which is the vertical direction. So let me just do 290 kips, and I'm gonna assign it to each one of the nodes where I am applying the girders in the superstructure. Dead load, and here you can see it automatically generated. If you want to see them graphically, you can, from the worktree, you can just hit display and the program is going to show you the magnitude of the load. If you change the unit, the program is going to automatically change the unit of the load applied. Let me just change it to kips. So after that, you can also see the different types of supports that you have applied graphically. You can see the sections, you can modify them if you need to right here, and so on. You can also add directly from this work stream, so it's up to you how you want to use the program in that matter. So from there, what I'm gonna do is I'm gonna save the model. You can easily come just to save it or save as, and then you locate the model, and then you can easily just run it and see the different types of values that you can get. It took about 2 seconds to run this particular analysis, and then you can just jump into the results. If you have any load combination, you can generate them automatically as per the ASHTO standards or different codes, as you can see here. ASHTO RFD we have available. We have different Canadian and European codes, and here the program generated basically different load combinations just using the dead load, as I mentioned, which is the one that I generated. Let me just transfer these to the concrete design tab, and then there the program uses them for the design portion of it. So let's check some of the forces that we have regarding these pier, and then we can jump into the other type of modelings. So let's say for the dead load, we can check the deformation, or you can see the different forces. Let's say the actual forces on the beams. Fx, which will be the actual direction of the piers, and you can see here the different forces that are generated due to that particular load applied on the top. Let me just change the view, and let me just lower a little bit of this. You can see the load applied. You can also check the reaction forces in X, Y, and Z direction due to that particular dead load apply, or the different load combinations for that matter. You can also obtain let's say a deformation contour of this particular dead load. So as you can see here, you can exaggerate the deformation. Let's make it a little bit more exaggerated, and you can see how the program is behaving in that. Let's check the inches, as you can see here, for that particular dead load. You can also show the deform displacement contour, so you can graphically see how the pier is behaving and where is it deforming to for each of the different loadings that are applied. From there, you can run the design in the program. You can do the design directly, or you can do the code check depending if you have the reinforcement or not. You can select the code that you're gonna use. If you have seismic provisions, you can also apply them, and then you can either do the beam design, let's say for this one, and the program will show you graphically how the design should be for that particular in this case the cap. As you can see, the program provides you the reinforcement to use and the area of reinforcement, along with the capacity bending and the shear capacity provided by that particular reinforcement that the program recommends you. If you want to do the design of the columns, which will be these two here, you can also perform it in the program, and you can get the graphical results such as this one with the area of reinforcement, the PM interaction diagram, the shears capacity due to that particular loading. You can also obtain the PM curve graphically, as you can see here, with that particular reinforcement that you provide, the program recommends. Or you can do something called the code checking. In this case, you can tell the program how many bars you want and the sizes of them and the spacing of the stirrup, and the program is gonna just provide you with the depending what the cover is for you, you can tell the program just to redraw it, and it will graphically show you the reinforcement, and then you can use that for your design check. That's about it for the pier. We can also perform the pier design using Midas GSD. In this case, you can obtain a PMM curve for design. You can obtain the moment curvature. If you want to do into more detail design, you can obtain the unconfined, confined, and consider it for the design. We have different nonlinear properties for the concrete and the steel that the program can take into consideration when you are designing a particular section. In this case, what we're gonna do is we're gonna model a hollow section, so just to have a variation of the different parts of the structure, and just to show you how you can use the GSD to do that. So let me just go back to the program and let me just open the GSD. You can go to the Tools tab, and the program has the General Section Designer, which is this one right here. Let me just show you, pull it up. This is gonna show you us how we can design an irregular hollow reinforced concrete section as per AASHTO RFD 2012 using the GSD basically. So let me just show you how we can start generating the section. So in Midas GSD, we can define the material as this one, and let me just add the reinforced concrete using the ASTM, and I'm gonna add a 6000 psi concrete. I'm gonna also add the use nonlinear materials, and in this case I'm going to use the Mander model. We have different types of material, nonlinear materials in the program, but I'm just gonna use the Mander model in this case. Gonna hit OK and OK, and then close here. I'm gonna change the units to keep inches in this case, just so that we are on the same page. And then I'm gonna generate a section, a hollow section. So in order for me to generate a section, I can use the drop down menu and use the shape, a basic shape. In this case, I'm gonna use a box, which is this one, and I'm gonna use the function for user defined dimensions. So I'm just gonna assign the different dimensions of the hollow section. The program automatically names it, and then I'm gonna assign the material that I just defined, and I'm gonna provide it the insertion point. If I here apply, the program is gonna generate the section as you see here. Perfect. From there, what I'm gonna do is I'm going to define the materials for the rebar that I'm gonna use. I just defined the materials for the concrete. I'm just gonna go ahead and define the materials for the rebar. In order for me to do that, so let me just define the rebar material property. I'm gonna use ASTM, and I'm gonna use grade 60 for the concrete. In this case, I'm gonna use the bilinear model for the strain curve, which is this one, and I'm just gonna hit OK. From there, I'm going to assign the rebar into the section. So in order for me to do that, I'm gonna use the rebar, and I'm gonna use the rebar perimeter pattern. In this case, the program automatically generates the rebar. I'm gonna use the number 11, and I'm gonna use 3.3 inches for the cover. I'm gonna use 69 rebars, and I'm just gonna apply it. Let me just select the shape that I'm gonna assign it to, which is this one. I double click on it, and then I just hit apply, and that's it. There, the program automatically assigns the rebar information, the rebar pattern, as you can see. Let me just fit the section right there. And then from there, what I'm gonna do is I'm going to define the code with the resistance factors, and then I'm gonna apply some load combinations from the some type of analysis so I can insert in this section. So in order for me to define the design code, I can go to the option tab and define the $RFD with the compression control and tension controlled resistance factors. They come automatically. You can modify these factors, and then from there I'm going to assign or define the load combinations. So let me just define them manually here. You can copy and paste an Excel sheet, but in this case I'm just gonna assign just some of them. You can define these load combinations manually, as you can see here. I'm just gonna define 2 just for the sake of time, and then from there you can use the design function so that you can obtain the interaction diagram. So you just hit the design section function. Let me just save this model, and then from there we can design the section using those load combinations that we just assigned in the program. Here the program shows the interaction curve. You can define different degrees, and the program will show you in 2 dimensions the behavior of the PM curve. You can also use or define the PM diagram depending on the code. In this case, the program provides us with the capacity of the section and the capacity as per the code with the different factors that we just assigned to it. So the program gives you 2 curves you can refer to for the design of this particular section. You can also draw a 3D curve and the program is gonna give you the behavior of the section due to the different load combinations. In this case, I only have two of them. As you can see here, this is load combination 1 and this is load combination 2. You can see the ratios in this table. If you have more, the program is going to show you more of them. You can show all of them, as you can see here, or just select a particular one and display it. You have two functions, two options right here. These are the two particular load combinations, and you can have as many as you want. And then let's do the moment curvature. So you can go to the moment curvature tab and define a load. Let's just define a 100 kips, and let's just generate the particular maximum strain, and let's generate the moment curvature. Here you can see the different points, where the cracking starts, where the concrete yields. Also, you can see the idealized yielding in the model, and from here you can change the strain diagram as you move along the different parts of the curve. So from there you can export this or generate a report. The program here generates a report in Excel that you can use. And then you can locate the particular file and just open the report and see how it comes out. In this case, the program can give you an Excel sheet like this one with the different informations from the general section designer. Here you can have an idealized this is just a report in Excel that at the end you're gonna generate, and the program can automatically do that for you. So that's a big plus. And you can generate even a stress contour for the particular load combinations and load cases. As you can see here, you can get the stresses for the material, the mesh, you can get the stresses for the rebars, and so on. So these are some of the functions that you can use in the journal section designer. And now to wrap up with the Midas, we're gonna use the talk about a little bit the bearing modeling. In the program you can model the bearing, as I mentioned, with the different stiffness in each direction. You can either do supports where as I did, we fixed the bearings. You can do also point springs that define the soil properties. For the supports you can constrain the degrees of freedom. These are the nodal boundary conditions. You can also do elastic links or general links that define bearings with the stiffness, or in case that you have, let's say, a triple pendulum system, we have it available. I'm gonna show you now. Also, we have the element boundary conditions, such as the beam and releases. We have the rigid links. We have that basically release some of the degrees of freedom or connects rigidly the elements or the nodes. And then we have for the elastic link, these are used to define elastic bearings of a bridge structure, which separates the bridge from the deck piers, as I mentioned earlier. We have the general ones where we can define the stiffness in each direction and translational and rotational stiffness. We have the rigid ones, which is the one that we use, connect two nodes with an infinite stiffness. We have the tension only, compression only, or multilinear to define the soil boundary conditions. We have also the general link. In the program we have elements types such as spring, dashpot, spring and dashpot, or the force type. which is we have the viscoelastic dampers, hysteretic systems, seismic isolators such as lead roller bearing isolators, or the friction pendulum system that's used in the West Coast, the high seismic zones in the U.S. Also, for the another type of part of the substructure is the footing or the foundation. We have a program called Midas Design Plus that defines different elements, structural and non-structural elements. In this case, we have a function for the isolated footing that we can use to define combined footing, strip footing, or just the isolated one. Let me just go ahead and jump into and here you can see that it is very similar to the GSD in the sense of the menu. We also have the kind of a work tree as in Midas Civil where everything is listed. You have the different members for design here, and let me just do the isolated footing so that you can see it right here. In the Design Plus, you can define the materials, you can define the loading, you can bring different load combinations. As I did, you can copy and paste them from Excel if you want to, or you can just put them in directly right here. You can also define a surface load with the different height, and you can tell the program whether you're doing with piles, you're using just a mat. You can, if you're doing piles, you can define the location of the piles, as you can see right here, how many piles you're using and the distances in between them, and so on. So that way you can arrange them, or you can just do the mat isolated one. If you want to do an eccentricity, you can define an eccentricity. As you can see here, you can define the section of the column, whether it is a column or a circle, and you can see them directly on this particular diagram. You can run a design check, or you can run a design directly, and you can see the different capacity results of it, or ratios. Let me just increase a little bit the soil capacity so we don't have that problem with the soil bearing right here. But yeah, you can see that the program provides you with the ratios, the design ratios. You can also see that the program can generate a drawing for something like this, where the program provides you with the CAD drawing, and you can save it as DWG, DXF, depending on, or that image if you want, as a matter, if you want to generate the drawings for it. The program also has a mode, which is the check mode, where let's say 3 different persons are working in the same particular project, and you want to check somebody else's job work. You can do a summary check, or a detailed report where the program provides you with the different equations used for that particular design or of this footing, for example. Moment capacity, shear check for the rebars. The same thing you can do with the columns. Let me just show you. If you have a column, let me just change to project mode. You can define different types. You have circular, you have rectangular, you can even add a general one, such as this one, where you can do the design for it, and the program is going to give you the same report. Also, it's going to provide you with the drawings. Even with the quantities, the program gives you the quantity of rebars that you're using for that particular project. As you can see here, you can also generate a member list. If you have multiple members, you can design them all at the same time. You can define the properties in a table, you can copy and paste it, export to Excel. All of our programs are compatible with Excel, so you can also do that and export it. and then from there you can design these particular elements of the substructure. So we've seen how you can do substructure only in Midas. It's a very easy way of doing it compared to the other programs out there. You can do the design also integrated in the same platform, and you can basically do whatever you're doing plus the superstructure, which is gonna be covered in the next section. So thank you all for your attention, and I hope you have enjoyed this session.